Swayam Prabha. Digital India. Educated India.
Hello students, welcome to this lecture. In this lecture, we are going to discuss about one particular spectroscopic method, that is the vibrational spectroscopy. We know that when a molecule has suppose n number of atoms, so to define this molecule exactly, we need 3n number of coordinates, because for each atom in this molecule we need 3 coordinates. So, therefore, for n atoms we require 3n number of coordinates. But once the molecule is formed, for example, there are certain bonds that are already defined, which goes into the definition of the molecule. So, therefore, not all 3n coordinates are essential. Rather, what happens is that if we define the center of mass of the molecule, for example, then we can define the location of the molecule or the center of mass of this molecule at a particular point in phase space. So, therefore, to define this center of mass, we can devote 3 coordinates, because the center of mass of this molecule will have an x coordinate, y coordinate and z coordinates. So, out of these 3n degrees of freedom, so we dedicated these 3 degrees of freedom as to locate the center of mass of this molecule. Now, once the center of mass of the molecule is defined, we can rearrange the molecule by simply rotating the molecule or reorienting the molecules. For a non-linear molecule, we actually require 3 additional degrees of freedom to uniquely define the proper orientation of a molecule. So, therefore, 3n minus 3 after taking care of the center of mass, and now 3 more degrees of freedom to define the orientation of the molecule. That leaves us with 3n minus 6 number of degrees of freedom, using which we can define the molecular vibrations. So, these 3n minus 6 degrees of freedom or molecular vibrations represent the motion of atoms within a molecule without changing the orientation of the molecule or without changing the center of mass of the molecule. So, therefore, for an n atomic system, n atomic molecule, we have 3n minus 6 number of vibrational degrees of freedom, and of course, for linear molecules, since we can require only 2 degrees of freedom to define the rotational motion. So, therefore, we have only 3n minus 5 number of vibrational degrees of freedom. Now, when a molecule undergoes vibrational motion along one of these vibrational degrees of freedom, the molecule is likely to change its dipole moment. Now, when the molecule changes dipole moment during undergoing this vibrational motion, this is a useful information for us, because now we can see that our molecule is ready to interact with electromagnetic radiation, because if a molecule changes its dipole moment by undergoing a particular change, we can use electromagnetic radiation to carry out this particular change in the molecule, and thereby the molecule or the matter will interact with the radiation. So, light matter interaction becomes possible, and then we can use a spectroscopic tool to determine more, to understand more about the molecular degrees of freedom. So, now we have this, in today's lecture we will discuss how we can use molecular vibration and use them in a spectroscopic method. So, we know to carry out this spectroscopy, we require a certain wavelength or a certain frequency of the electromagnetic radiation. Now, we should have that particular electromagnetic radiation whose frequency or whose energy matches with the difference in the energy levels of these degrees of freedom that we are interested in. Since we are talking about vibrational degrees of freedom, typically the vibrational degrees of freedom by vibrational energy levels are separated from each other by, let us say, 100 wave numbers to a few thousand wave numbers. So, this energy range in the electromagnetic spectrum, we have already seen, corresponds to infrared region. So, if we use infrared light or infrared radiation, we can actually induce molecule to a molecular vibration, or we can force molecule to undergo vibration, because we are providing the adequate amount of energy. And now, the moment molecule undergoes this vibration, the molecule starts interacting with the light, and then we can obtain molecular information through regular spectroscopic techniques. So, this is what we are going to discuss today, but before we go for polyatomic molecules where there are a large number of degrees of freedom, let us first confine our discussion to diatomics for simplicity, and then we go to the next more complex systems. Now, we consider a diatomic molecule of the type AB. So, to keep it general, we are taking the two atoms in the molecule to be different. Suppose the equilibrium bond distance of this molecule is Re. So, since this is a diatomic molecule, total number of atoms is 2. So, therefore, the number of degrees of freedom is 3n minus 5, which is equal to 1, and this degree of freedom is simply this bond distance. So, we can change this bond distance. For example, I can shrink this bond AB by making it the distance becomes Re minus x, or I can stretch this bond by making it Re plus x bond distance. So, therefore, I can change the bond distance, and this is the degree of freedom that I am talking about. So, now we see that here this motion implies that I have an equilibrium geometry around which the molecule undergoes the vibration. So, either it shrinks the bond or it elongates the bond. So, this is a typical example of harmonic oscillator problem. So, to define this, you should remember that we use the harmonic oscillator potential. So, by which we defined as V equals half k x square, where this k is the force constant corresponding to this bond. So, now since this is a harmonic oscillator problem, we already know the solution of harmonic oscillator problem, and therefore, we can use the harmonic oscillator solution to describe the vibrational motion of this molecule. So, what do we know about the results of harmonic oscillator? So, one thing we know is that the vibrational energy level or the energy level of a harmonic oscillator is given by V plus half h bar omega, where omega is the vibrational frequency associated with this particular vibration, and in this case this is a stretching frequency, and V goes from 0 to large numbers. So, it goes from 0, 1, 2 and so on and so forth. Looking at this energy expression, you can see that the lowest energy which corresponds to V equals 0, its energy is half h bar omega, the next one is 3 half h bar omega, next one is 5 half h bar omega, with the energy difference between two consecutive levels is constant, and that is simply h bar omega. So, this is about the vibrational motion that we harmonic oscillator energy levels. We also obtain the eigenfunctions corresponding to the harmonic oscillator problem. So, the eigenfunctions were given as some normalization constant and Hermite polynomial of Vth order. This V corresponds to the vibrational quantum number here. So, this is Hermite polynomial of Vth order multiplied by we had something e to the power minus x square by 2, where x is the coordinate along which this harmonic oscillator is defined. So, for example, if I define this as the bond length, so if this is R, this is Re, this is the equilibrium geometry, and if I express the same in terms of x. So, if I describe it in terms of x, which x is the elongation or stretching or the distortion from the equilibrium geometry. So, at equilibrium geometry it is 0, and towards the left and towards the right its value increases accordingly. So, x goes from minus infinite to plus infinite, where x equals 0 represents the equilibrium bond distance. So, these are the vibrational states that we have. Now, when we do vibrational spectroscopy, so these are the vibrational energy level. Now, we shine a radiation on the molecule. We as we discussed, since the energy levels in typical molecular systems with vibrational energy levels, they range between a few hundred wave numbers to a few thousand wave numbers. So, therefore, we are going to use infrared radiation to to induce this transition. So, what do we mean by that? Suppose we want to do a transition from an arbitrary state V double prime to V prime. So, what we would do is that we would try to find light whose energy would correspond to the difference between the energy level of V prime and V double prime. So, for such a transition to occur, we need to see a few conditions, and this is what we are going to discuss next. To see whether a particular transition occurs or not, we would define something called transition dipole moment. The transition dipole moment is defined in the following way. Suppose I want to start from a state psi v prime and I want to go to a state psi v prime. So, this is my initial state and this is my final state. The transition dipole moment is given by this integral forgive me, this prime should represent so this is the initial state, this is the final state, and this one is the electric dipole moment of the molecule. We will come to the situation why we are writing in this way, but we can equivalently write it in bracket notation. So, this is the transition dipole moment. What this tells? This tells that I am considering a transition from psi v double prime state to psi v prime state, which are two vibrational states, and the operator that couples them is the dipole moment of the molecule. So, where mu is defined as the electric dipole moment of the molecule. Now, why do I have this mu over here? Because when light or electromagnetic radiation falls on matter, the matter must communicate, the molecule must communicate with the light, and how does it do? It communicates with the light through its electric dipole moment. So, therefore, this mu enables the molecule to undergo this transition from psi v double prime to psi v prime. So, therefore, if mu is absent, if mu is 0, the transition dipole moment becomes 0. Now, what is the significance of this transition dipole moment? Because we would see that intensity of a particular transition would depend on would be proportional to square of this transition dipole moment, this integral. So, therefore, if mu becomes 0, R vanishes and therefore, intensity becomes 0. So, therefore, this transition is not allowed. What kind of system we would have mu equals 0? For example, since we are discussing about diatomic molecules. So, if I consider a homonuclear diatomic, for example, like oxygen molecule. So, if I have a 2 type system, a type of system. So, therefore, this molecule will have no dipole moment, and since the molecule does not have any dipole moment. So, therefore, it is going to be infrared inactive, or it will not show any vibrational spectrum. Of course, when you go to polyatomic molecule, the situation will change slightly, and we will discuss more on that part over there. Now, let us come back to our situation where it is not homonuclear, rather it is heteronuclear. So, I have the 2 atoms are different. So, since the 2 atoms are different, so therefore, mu is not 0 here anymore. Now, considering the case where mu is not equal to 0, now if I have taken a B type of molecule, suppose carbon monoxide or nitric oxide, if you take, you can experimentally measure the dipole moment of this molecule. But the outcome that you would get would represent the dipole moment of this molecule in its equilibrium geometry. But we know that when the molecule is undergoing vibration, its dipole moment is going to change. For example, consider let us make this plot where I am in the x axis I am plotting r, the internuclear distance, and in the y axis I am plotting mu. Suppose to the limit when r becomes 0, that means the one atom is the hypothetical situation where one atom is exactly over the other atom. So, therefore, since the two charges are not separated, so that the dipole moment does not exist. So, it becomes 0 at this limit at a small value of r, and similarly at large values of r when a and b are far away from each other. So, therefore, they do not know each other, they do not interact with each other. So, therefore, that they can be approximated as two independent atoms. So, therefore, at that situation also the molecular dipole moment becomes 0. So, therefore, at low r goes to 0, the dipole moment becomes 0, r goes to infinite, the dipole moment becomes 0, but of course, we know that since it is a heteroatomic molecule, at equilibrium value it has, at equilibrium geometry it has some finite value of dipole moment. So, I am plotting a curve like this. Of course, I do not know the exact shape of this curve in the intermediate values of r, but what I understood is that at r equals 0 and r equals infinite, the dipole moment becomes 0, and for the intermediate value of r, the dipole moment is finite. Exactly how it behaves, I do not know, because it would depend from molecule to molecule. Now, since we want to prescribe a method which will be applicable to all types of system. So, therefore, let us try to find out how we can define mu for different values of r. Why are we interested in different values of r? Because we are talking about vibrational spectroscopy where the bond distance is going to change. So, it is not enough to know the dipole moment at the equilibrium value. Suppose this is my equilibrium value R e. So, I know that this is my dipole moment at equilibrium value. So, let me call this value as mu e, the dipole moment at equilibrium value. But for in vibrational spectroscopy, it is not enough if I know only mu e, because I need to know how the dipole moment is going to change when I change the bond distance or a particular degree of freedom. To be able to provide a general description, therefore, I am going to expand this mu, the dipole moment, as a Taylor series expansion. So, where I say mu equals mu e, which is the equilibrium dipole moment, plus, and then I expand this mu in the order of r, or here in this case, since I have defined x as my coordinate, which takes me how much am I deviating from the equilibrium geometry. So, therefore, I am going to define something like this at equilibrium multiplied by x plus half and so on. So, this is the first order term, this is the second order, this is the, and then I can write as third order, fourth order. So, what this term tells? This is actually the dipole moment at equilibrium value. This term over d mu by dx, of course, I am using partial derivative just for general purpose, but since I have actually in this example that I am discussing, I have only one degree of freedom. So, therefore, only one possible value of x. So, this partial derivative is equivalent to normal derivative. But for general sense, when I have multiple degrees of freedom, that would be partial derivative. So, now this d mu by dx is essentially the slope of this mu curve at r equilibrium, at the equilibrium geometry, what is the slope of this. So, therefore, this value d mu by dx, the first derivative of the dipole moment is going to change from molecule to molecule, because this is molecular specific information. And what about this term? This is the curvature at r equilibrium, the curvature of dipole moment against the coordinate at r equilibrium. So, this tells the curve, this gives talks about the curvature, this talks about the slope. So, this is how I define my mu. But what do I do with this dipole moment? Because this dipole moment is responsible for taking my system from psi v double prime to psi v prime. To do that, let me go back to the transition dipole moment expression. So, I have this r, which is given as this term here. Now, let me put psi v prime mu e psi v double prime plus, since this is going to be a slope. So, therefore, this is a constant for a particular molecular system. So, I am keeping this out of the integral, and and again this is the curvature, which is again going to be a constant. So, therefore, I am keeping it out of the integral, and then I have higher order term. So, this is how I see the transition dipole moment to be developing. Now, let us look at the first term. Mu e is a constant. So, therefore, I can bring this out of this integral. When I bring this out, you would see that the remaining integral will become simply an overlap integral between psi v prime and psi v double prime. So, we know that psi v prime and psi v double prime are two states of the harmonic oscillator. A harmonic oscillator problem was the Hamiltonian was a Hermitian operator. So, therefore, its eigen functions are going to be orthonormal. Therefore, if v prime and v double prime are different, so therefore, these two wave functions are going to be orthogonal to each other. So, this becomes delta v prime v double prime. So, only when v prime is equal to v double prime, this will become 1, otherwise this is 0. Now, since we are talking about a transition from one level to another level, so therefore, necessarily v prime is different from v double prime. So, therefore, these two functions are orthogonal to each other. So, therefore, this term becomes 0. Now, I am left with the higher order terms. So, I have this constant and I look at this term over here. I see that I have this particular integral, which shows that this has psi v prime in the bra x and psi v prime over there, and psi v prime and psi v double prime are harmonic oscillator based functions, which are given by Hermite polynomials multiplied by the normalization constant and e to the power minus x square by 2. So, therefore, to evaluate to look at this particular expression, I am going to use the property of Hermitian operator, in particular this recursion relation of Hermite polynomials, which says that the Hermite polynomial of v plus 1 order is equivalent to 2x multiplied by the vth Hermite polynomial minus 2v of v minus 1th order of Hermite polynomial. So, how would I use this? Let us try to do this. Suppose I want to work on this expression over here. So, I can rewrite this equation as the following: h v in this case becomes h v plus 1 2 x h v equals h v plus 1 plus 2 v h v minus 1, where this h are the Hermite polynomials. Now, we see that x h v is expressed in terms of the v plus 1th order and v minus 1th order of Hermite polynomials. Remember, this v is just the vibrational level. So, therefore, this is merely a number. Now, we will look at this integral over here. So, let us let us look at this psi v prime x psi v double prime. So, in this case I am writing would be so this is psi v double prime is essentially we are only going to consider the Hermite polynomial. So, therefore, I have in the bra side h v prime, and the ket side we have the first term h v double prime plus 1 plus 2 v h v prime, forgive me, there is no 2 v h v prime h v double prime minus 1. So, I am just replacing this x psi v double prime using this relation, and now I see that I have got two overlap integrals. The first one over here shows the overlap between v prime and v double prime plus 1, and the second one is overlap between v prime and v double prime minus 1. Now, we know these Hermite polynomials are again orthonormal. So, they would become 0 unless v prime and v double prime the bra and ket are not same. So, therefore, this the first integral will survive only when v prime is equal to v double prime plus 1, and the second integral will survive only when v prime is equal to v double prime minus 1. So, therefore, v prime is only these two conditions, this integral will survive, and therefore, this would for all other this integral would also survive. For all other values of v prime and v double prime, this integral will become 0. So, this gives us a selection rule. If you see that delta v becomes plus or minus 1. So, this is a selection rule that we obtained by using the property of the Hermite polynomials, which are the eigenfunctions which we use to define the eigenfunctions of the harmonic oscillator problem. So, we got this delta v plus equals plus minus 1 as the selection rule for this this term over here. Now, if I consider the second term, which is written over here, which is being coupled by x square operator, you can use this expression twice, and then you would see that that delta v equals plus minus 2 will survive, and for all other delta v values this integral will become 0. Now, let us come back to our discussion. I will just erase this particular derivation. And to continue our discussion, we see that this is the this term is the first derivative of dipole moment with respect to x, and now this integral survives only when delta v equals plus minus 1, and this integral will survive only when delta v equals plus minus 2, and similarly you will see that the higher integrals will survive only when delta v equals plus minus 3 and so on and so forth. Now, that is one selection rule, but what we would see now, the dipole moment, when you are expanding this dipole moment as a Taylor series expansion, it is often enough if we truncate this series just after the first order. Therefore, in other words, we ignore the second order and higher order, second and higher orders. So, therefore, our r value or the transition dipole moment simply truncates over here. So, this gives me d mu by dx at equilibrium So, if I truncate this, so this is called harmonic approximation. In this case, under harmonic approximation, the selection rule becomes delta v equals plus minus 1. Of course, when delta v equals plus minus 2 comes, that means when we go beyond this harmonic approximation, we get we'll have the higher order term, higher order transitions, but at the moment we see that delta v equals plus minus 1 is the selection rule. Now, considering this delta v equals plus minus 1 selection rule. So, if you remember, we had the harmonic oscillator v equals 0, 1, 2. So, delta v equals plus minus 1 means I can go from 0 to 1, or I can go from 1 to 2, or I can go to from 2 to 3 and so on so forth. So, suppose I go from 0 to 1, what would be the energy that the system will absorb? I know that these are all the energy separation are all similar, and that is h bar omega. So, therefore, whether I make 0 to 1 or 1 to 2 or 2 to 3 transition, I would always see one line, and that line would appear in spectrum at h bar omega, because all these energy levels are equispaced within delta v equals plus minus 1 selection rule. But then there is one more thing. Suppose, how do I know that whether it is actually happening from 0 to 1 or from 1 to 2 or from 2 to 3? To answer that, we would see that although the molecule can absorb h bar omega radiation and go from v equals v to v equals v plus 1, does not matter what value of v, but molecule will be able to do that only when the molecule exists at the vth vibrational level. So, let us find out how many molecules are there in which vibrational level, and to do that we use the regular Boltzmann distribution which is applicable for system in thermal equilibrium. So, we try to find out what the population of number of molecules at Vth vibrational level compared to number of levels which are 0th vibrational level. This is given by simply delta E divided by kBT, where kB is the Boltzmann constant, T is the temperature at which you are doing, and delta E is the energy difference between Vth energy level and the lowest energy level. So, this delta E is actually the difference between the two levels, difference in energy between these two levels. Of course, we are currently not considering the degeneracy, because we know in case of one dimensional harmonic oscillator all of them are non-degenerate. So, therefore, this would not matter. For an example case where delta E is suppose 1000 wave numbers and temperature is considered 300 Kelvin. So, if you plug these values, you would see that e to the power minus delta E kVt would become e to the power minus 4.8, or which is roughly equal to 0.008. So, that means this is NV. So, that means if the energy difference is 1000 wave numbers, which is often 1 degree of the value of the vibrational frequency of a typical vibrational mode. So, when delta E is 1000 wave number, that reduces that the population at V equals 1 is 0.008 times the population of V equals 0. So, that means so few number of molecules are present at V equals 1 level, and if I go to V equals 2, so that means the energy will become 2000 wave number. So, you would see that this number will become 10 to the power minus 6, or at least of that order, and as I go higher and higher energy level, the population of these higher levels will become very, very low. So, for practical purposes, V equals 0 is the only populated state. All other higher vibrational levels are barely populated. So, we can ignore them. So, therefore, when I see this band happening at h bar omega, I know this is happening mostly because of 0 to 1 transition. 1 to 2 transition may occur, but the number of it would depend how many number of molecules are present in this case. Now, this is 0 to 1 transition at h bar omega is called the fundamental transition or the fundamental band. The fundamental transition. So, this is 0 to 1, but of course, we are restricting ourselves to the harmonic approximation. That means, we are truncating our dipole moment expansion just after the first order. So, therefore, we are not getting delta V equals 2, delta V equals 3 and higher order transition. So, within harmonic approximation, delta V plus minus 1 is the selection rule. However, suppose we consider higher order contribution of the dipole moment operator. In that case, what would happen? Delta V equals 2 or delta V equals 3 would also be allowed. In that case, 0 to 2, 0 to 3 transitions will also occur. So, 0 to 2, 0 to 3. So, 0 to 1 we called as fundamental band, and 0 to 2 we would call that as first overtone, or we also called it second harmonic band, and 0 to 3 would be second overtone or third harmonic. So, within harmonic approximation only 0 to 1 is allowed to be observed. Beyond harmonic, we can see first overtone, second overtone, and of course, these bands will appear at h bar omega, 2 h bar omega, 3 h bar omega respectively. What about their intensities? Their intensities will be much less compared to this h bar omega. Why so? Because intensity is coming as the constant that comes out in the dipole moment Taylor series expansion. The first order term, we had the slope of mu with respect to x. The second order is the curvature or the second derivative. which would be significantly smaller than the slow, and as you go third and fourth order, again that quantity will become much smaller. So, therefore, even when they are allowed, their intensities become much less. So, in this lecture we discussed about the vibrational spectroscopy. In particular, we focused on diatomic molecules where there is only 1 degree of freedom, and we see how we can define the transition dipole moment and obtain the selection rules within harmonic approximation. We got delta V equals plus minus 1 as the selection rule. Also discussed about the fundamental band and first overturn band, and we will continue our discussion in the next class. Thank you for your attention.